But the thing is that we don't just morph a mesh. We morph a CFD model ready to go. And usually we morph this when it's already in memory and it's already partitioned in thousands of locations in the memory on the nodes. It works and it's super fast. So going back to the Formula One, once you have your model in memory, you want to investigate 5 shapes, 50 shapes, 100 shapes. It's just a matter of the computational power that you have.
Today I have the pleasure of interviewing Marco Biancolini, the founder of RBF Morph. Thank you to RBF Morph for sponsoring this episode. Marco is an associate professor at the University of Rome, Tor Vergata. He has over 25 years of experience in numerical simulation and mathematical modeling, and today we discuss his innovative contributions to CAE. I hope you enjoy our conversation, and please like, subscribe, and hit the bell. Welcome to the show, Marco. Thank you for joining.
Thank you. So happy to be here.
Yeah, I'm really excited to talk with you today. But before we get into mesh morphing and RBF Morph, can you tell us how you got started in simulation and your background?
Yeah, very good question. So I'm an engineer, a mechanical engineer. So I started using FEA some years ago when we have a locked license of 5,000 nodes. So I'm not that old, but it was a long time ago indeed. And I started my research career in the university, and I was always involved in the technological transfer. And I started to work about fluids, doing fluid structure interaction with friends, expert in fluids. At the time, my expertise was more in the structural side. And so it happened that I started a project with the Formula One team. And so the results were so good that it was a pity to not introduce what achieved in the market. So I started my company at the first time as a one-man band. Then now we are 20 people working at RBF. So I am in the middle now. So I am today now in the research field. I am a manager of research. Of course, I am still able of coding. No, and at the same time in the company we support industries. So we are in a strange area, no, because it's always a problem to transfer knowledge from the research from the university to industry, because you have to understand the industry needs. And I'm a little bit in the middle of it. I have completed in July a 4-year project funded by AC about medical digital twins. And it was a Marie Curie project, and it was an European industrial doctorate. So in the middle between the research and the industry, this is where I feel myself comfortable.
Yeah. And I find that's a really unique space for many reasons to be. And can you just talk about, you mentioned it's difficult, right? It's difficult to transfer knowledge from research to the industry, but I'd like to dive into that a little more. What do you feel like makes it difficult to do that? Why do you think it's so difficult to do that? And then the second part of that would be, what did you do to do it successfully?
Yeah, not easy, and it's a nice question indeed. So the main problem, I think, is that when you are very good at research and you are focused on a specific topic, you are really on the topic and more on the topic than on the knowledge and expertise that you build around. In the industry, you need the solutions, and you need the solution right now, not tomorrow, not the day after tomorrow. So what is really important is to understand what are the needs of the industry and to adapt or reinvent from scratch a new solution. This is exactly what I did. I was a super expert about structural analysis, about optimization. Mesh morphing was not my business. But as a scientist, I was prepared. I think I'm quite good. Just let me admit, okay? So I was prepared to invent something new, because the need at the time was we want to move 1 billion mesh sized, no, because we want to change the shape. How to do that? So I starting from FEA, BAM, and then I met the radial basis function. Was the first. I was not an expert of radial basis function. at the time. So I think that for a good technological transfer, it's really important to understand the needs. Of course, the research hasn't to be 100% industry driven, okay? But if you want to pursue a technological transfer, and okay, you could invent something totally new, a new way to discover energy. Okay, it's not that common. Okay, what is really common is that we have brilliant minds that are able to tackle very, very complex applications. And in the industry, it's different because there is a different pace. And so even super brilliant minds could haven't the time to elaborate new ideas, new concept. So if you put this together, you can. With RBF Morph, we are doing great. So it was a good project. I feel a previous one. I had a previous company that was quite good. It was a motorsport technology for performance prediction of a go-kart. So yeah, so the industry was the ground one because in Formula One you have research. Karting is not that rich industry, so we have a very good tools, very good toys to play with, but there was not a research system of it. No? So moving from karting to Formula One, things changed, and we are here.
Yeah, that's really exciting. And I love that you emphasize that you didn't know about morphing and radial basis functions until you started looking at industry. Because I think as a student, especially, and maybe I might be unique here, but I think it's easy to look at someone's career and think, wow, look at what Marco's done. And they just the default assumption is, oh, this is what he picked as an undergrad to do. And they don't understand often how it comes. And I know I've fallen into that trap of you think that so it's just really, I love hearing these stories of how it starts and how you go about it, that you weren't familiar with it. And yet you've built a successful company around it. And
Yeah.
yeah,
I think that one important thing is that, first of all, you need to create some good reputation. No? So
yes.
with that Formula One team, we started in fluid structure interaction. We started with other activities. And the reason why at the time they were really struggling, because at the time, it was 2007, I got here. And at that time, no, the rules of Formula One were changing. I don't know if you remember, but in 2009, the cars totally changed. A
Okay.
very large front wing, a very small rear wing, because there was this undertake problem. So to allow to facilitate the Aero, no, to do the overtake maneuvering. And so in this situation, all the teams had to reinvent the car from scratch, a white paper to start. And so they decided to invest. It was a Formula One top team at that time in the mesh morphing technology, because it's a very fast tool to investigate hundreds and hundreds of variation. Today we see on the LinkedIn, you see daily objects that are changing, and we are saying that everything is AI powered. No, but at that time it was not the same story. So
Yeah.
they need a tool to do a lot of data crunching. And honestly, we started with a simple demonstrator, with a MATLAB demonstrator, and happy. So I put the MATLAB demonstrator into the Fluent custom UDF to make it working. And we started the project. So
Awesome.
it's a matter of adapt about the needs. And it's not just a matter of becoming an entrepreneur, no, because it's went. At the time, it was not an entrepreneur, no, and merely a consultant, no, but also for the research path, the research passion, no, having the ability to interact with advanced industry, because it's very high tech industry. So having the ability that your model, your ideas are run on thousands and thousands of core on a super APC, no, it's really rewarding. So you can have a very good part. But I think that the main point is to create the proper connection between what you're doing in research and what is in the other side. because there are many situations, especially in Italy, but I don't think it's just in Italy, maybe more in Europe, in which in academia, there are experts with super knowledge, that are curious about the knowledge, and are not really understanding what is the best path, the best route to shine. And also, all in all, if something is useful, it has to be used. So it's interesting, especially for us as engineer, we are working on computer science on object, and that can be used, transferred easily. And also another, of course, point that is typical of the PhD student that is a super expert in setting up algorithms. So if you have something that works, you are here, no? But to make a software, you have to go there. And all this part of the story is not good because you have quality testing, documentation, deploy, making the software working for super skilled people like you, but also for, daily engineers that are working with your technology, that they want to read the scientific paper. They want just a tool that does the job, no? So you have to learn many things, but it's really exciting.
Yeah. Yeah. Thank you for expounding. I love that statement. For something to be useful, it has to be used.
Yeah.
Yeah. Love that. I'm gonna quote you many times with that one. So we've touched on it. It's been a part of the conversation, but for someone who's listening and who doesn't know or understand what mesh morphing is, can you give a high level summary, just beginner's introduction for someone so they're up to speed?
We have two terms, mesh and morphing. So a mesh, generally speaking, is a tessellated representation of an object. And so there are mesh morphing applications that are used also in computer graphics, to move character, to have special effects, and so on. But if we stay in our CE world, that is the topic of today, mesh morphing means that you have typically an high fidelity model. That could be a CFD, FEA, electromagnetic, could be a combination of that. And what you should know is that the more is the complexity of your model, and the more is the time to have a new variant of your model. Okay, so mesh morphing could help. Why? Because mesh morphing means that your model topology stays exactly the same. So you have the same cells, the same nodes, everything is exactly the same, but you have a technology as the one we have, but there are others on the market that is able to move all the vertex of the mesh. So we call vertex in computer graphics. When we speak about FEA or CFD, we call nodes typically, no? And so the nodal position are updated. And when you update all the nodal position, you can achieve simple effect. For instance, we were talking about Formula One. You can simply adjust a flap. It's a single rotation, but it's not that easy to do. You can do something more advanced. So with the morphing, you can change the shape of a board or of a wax control because you want to achieve minimum drag, maximum lift, stability, and you have the KPI that are typical of your problem. So the point is, we need a technology that is able to quickly change an high fidelity model that takes a lot of time to be created. So mesh morphing is a way to do that. So it's not just, we say mesh morphing is good, you understand, but the thing is that we don't just morph a mesh. We morph a CFD model ready to go. And usually we morph this when it's already in memory and it's already partitioned in thousands of locations in the memory on the nodes. It works and it's super fast. So going back to the Formula One, once you have your model in memory, you want to investigate 5 shapes, 50 shapes, 100 shapes. It's just a matter of the computational power that you have. That today in Formula One, as you know, is capped. You can't investigate as many shapes as you want. We have rules for this. In 2007, this was not the case. You got some limitation about quantity of HPC you can use, but was different at that time.
Thank you. Thank you for that explanation. And I think that's something that isn't always clear to people, right? That it's not, you're not building a standalone solution. It has to be able to integrate to the team's workflow and their objective. And so I'd like to dive into this a little bit more because I don't understand. I'm not a CFD developer,
Okay.
haven't written as much code as others have. But can you walk through what that process actually looks like for a user using RBF Morph? So you talk about it's already in memory, it's already there on the computer. So what interaction would the user have to be able to sweep over maybe some shape changes and parameters? What would that actually look like on the user side?
Okay. Okay. I start first describing the first product that was an add-on for Fluent, the CFD solver, and then I
Yeah,
extend this. But at that time,
sure.
it was super simple because I got a very simple request to create the technology. The request was, I want to change the mesh with a single command line, and the command line should be, and it is, now it's with the commercial name, okay? It's RBF Morph, shape 1, intensity 1, shape 2, intensity 2, shape 3, intensity 3, as many shape as you want, push one button and good there. What is the meaning of the shape 1, shape 2, shape 3, and so on? Shape 1 could be rotate 1 degree of length. Shape 2 could be change the width of the wing of 1 millimeter, and so on.
Yeah,
Very simple. And our first logo, now the company logo is RBF, not just the RBF.
yeah,
But before it was RBF Morph with parentheses. And the reason of this logo is that in Fluent uses scheme, and the scheme command was RBF Morph. So we decided at the time to use this in the logo. So on the point of view of the workflow, you have two stages. There is the first one in which you have to describe to the software what is the meaning of the rotate of length. And here, the radial basis function technology enters because radial basis function is very powerful for mesh morphing for at least two reasons. The first one, it has all the benefit of the mesh-based method. You can deform a mesh, for instance, using an FEA solver. Why not? So using a mesh-based method, it means that you have the point-wise control of the shape. Consider that we can build up snow or ice with very complex shape using mesh morphing. We have these for aircraft, for high-speed trains, for car, as an example. So a shape that hasn't a cut, it's really, really a nightmare, as a shape to be represented. And this point-wise control is really very important and costly. And if you go with FEA, it's really complex because if you have 1 billion sized mesh, you need a 1 billion size FEA model. It's not possible, absolutely. And the other approach you have is that you can go with meshless method. A meshless method, it's a kind, I love to call it a space worker. So you have analytic defined function into the shape that are able to distort the space everywhere. Okay. And you can use, for instance, there are technology of our competitors that are using boxes. So you can put one morphing box and then you can pull the edge of the box and everything will follow. We use Bashline polynomial to this. It's called the FFD technique that was born in a General Motor at the end of 60. So there are many methods I have studied, of course, I'm an expert of this topic. So the very good thing of the meshless method is that whatever you have, you could have a tetrahedron, you could have an X, you could have an interface, you can have in FEA, you could have a contact surface. Whatever you have, it will work because it's just a space worker that bring the nodes all together in field. So it doesn't matter if you have a polyhedra, a tetra, or another element. Of course, you could destroy the element if the morphing action is not that good. No, because you can distort the mesh.
sure.
And there is another important point about the parallel run of thousands of partitions that once, I don't know if you are expert about HPC, but to solve a very large problem, what we do, we subdivide the large mesh, the large problem, many small domains that are speaking each other. So what is the problem? The solver is ready to do this, but when you morph, if the morphing is not perfect and you destroy the interfaces between the partition, you will be unsuccessful. So the good of using a meshless approach is that this field works perfectly in parallel. So we have a parallel implementation with OpenMP, with NPI, with CUDA. It doesn't matter because it's easy. It's easy because it's intrinsically guaranteed by the method. Okay. And so the RBF are really a very good solution. And many vendors now are introducing RBF. No, even the big names. So this is the reason why radial basis function mesh morphing is good, because it brings together all these benefits with one drawback that is really difficult to scale up. I remember when we started in the Formula One team, first problem, 1,000 points to control, easy. 10,000, less easy. 100,000, 1 million, 10 millions. Now we can go up to 10, 20 millions of RBF points. And it's not easy because if you go in the math of the RBF and of the RBF that we use to have a good quality that are full supported RBF, the problem is that the standard program scale up with the power of 3 with respect to the number of points. So you will soon go out of business, out of memory, out of performance. Yeah. And so you need a lot of much. And we put everything in space partitioning. We use fast multipole solution that is the same math that is used to study, the universe. So there is a really complex math behind to make this working. But step by step, we managed to have, I think, one of the fastest RBF solver out there. So this is one of the major limit. And so if you start with RBF, there are many papers now there. I have started in 2007. That was just a couple of papers. At that time, now there are many. I wrote a book about this. And, today it's really difficult because if you start to do everything on your own, going up to the much able to go up. But this is true also if you try to write out a CFD solver, an HGH solver. Now, you can do simple things, but to go high with the size of the model and everything, there are so many. It's not just a matter of how you code and how you have fast resources. There is a lot of secrets of algorithms and things that needs to be put together to have the right solution. But yeah, it's so fun work on this.
Yeah,
it's really rewarding, because you have the puzzle to solve. And so once, we have now a new version, we put the new version of the solver inside that was not stable enough. So we wait. And then we made a 10x on the performance, and 10x, it's really a lot. So it's interesting. And we see what's going on. You see, for instance, now we were talking about Fluent and the GPU implementation that now it's exploding as a really promising technology. So it's really a fantastic work, this one.
Yeah, just coming back to the load balancing, I remember this was a couple of years ago working on a job and we were using AMR and we were tracking a free surface and the partition, I would try to monitor and I think I was using Fluent at the time for this project at least. And we were trying to do some load balancing because you'd get the AMR splitting way more cells on the partition and trying to do that. And so just to clarify for my understanding, what you're talking about is we keep the same mesh and all of the math in the matrices stays the same, except the vertex values. The relationships between the topology is what stays the same, and which is what allows the partition. In theory, if you had your partition perfect how you wanted it and you're just morphing, you now have the same communication lanes open in that partition because you've only moved the nodes but the faces are still talking
Yeah.
and sharing information that way. So yeah.
We can be more specific on this if you want.
No,
So,
sure.
for instance, in Fluent, it's very easy because with Fluent, we have UDF functions, and UDF functions are already for parallel implementation. So it works like this. So let's say you want to shape modification to make things easy, no? The one and the two. Okay, so you prepare them. And now you prepare them, you can interact with a UI, no? Or you could simply create a script that prepare your setup. It's quite common, no? So once you have to do always the same thing, you don't want to push button, no? So you create a script that prepare your solution and store the data to do the morphing. Once they start the data to do the morphing in RBF Morph for each shape, we have twice. One is an ASCII file with all the information about the morphing, and one a binary file with all the RBF points and all the field stored already to be amplified. So once this is there, no, you can simply load this into Fluent with the UDF in parallel Fluent. You spawn this information to all the partitions. So each partition will have the full shield. No, so the partition doesn't know about the field. So the field in each partition is for all the mesh. Okay, but it's a very lightweight information. So we have the problem of memory of this.
Sure.
And then we decide the intensity, and the ability to change the intensity is something that is not requiring the recomputing of the RBF. So it happens directly at runtime. So each partition, all the nodes ask where I have to go, and the RBF solution tell you go there. Okay, and this includes also do nothing, because we to save resources we use to create domains to limit the area that has to be more like, you know, like in the cavity remeshing. No, so you decide that you have the tree. It doesn't matter that you touch the mesh that is meters on the other direction. So you can wrap, and so it will happen that just the partition that are there will work. And so we have another optimization because we want to go faster. So what's happening in RBF Morph is that once the partition that needs to morph asks, okay, we take the job for morphing and we spawn the job to all the cluster to do faster. And it was a nightmare to code it, but it works like this. Okay. But in other solver, for instance, in Helix and OpenFOAM, we use a different strategy because we create the morphing field straight in the parallel file system, because in that case, you have that the mesh is already partitioned at file level. And so we can morph the nodes on the parallel partition and read, or we can create, for each partition, we create the local field. So at runtime, the partition will ask to the storage field the job and will move. So it's quite tricky, but it's really very HPC interconnected. And you have also to add that in all this story, you have the complexity of the algorithm, you have the complexity of the fluid solver and so on, but also the IT complexity to make this working. It's really hard. We are, veteran, I can say, of Fortissimo, that is an HPC project. We started with the very first Fortissimo in 2013. The first project we did was the optimization of an airbox for the Lamborghini Aventador. And the rationale was that we want to use additive manufacturing. And so we want to produce a kind of a sexy shape to reduce the pressure loss, and we managed to got 6% power more of an engine that has so many horsepower, so that I don't remember, something like 600, 700. So 6% is like my car, no? So really a huge power. And so at that time, the challenge was of this Fortissimo HC project. Fortissimo is a project that fosters the use of HPC in the European industry, no? And it funds small experiment demonstrators showing how the HPC could help. So we started with automotive, and we put on the cloud an automatic solution that was based on Fluent. to do this optimization. Then with the same Fortissimo 2 was the name. Some years later, we do an automated FSI optimization for an aircraft for Piaggio days. And then we moved recently in the FF for Euro HPC. That was the last call name. And we did 2 medical projects. One was about the simulation of the surgery. So creating the medical digital twin of the surgery. So more, a topic that is very, very important today. So a different use of HPC, because in that case, you use morphing to create variants. So let's say it's about the modified blood casting that is a surgery that is done on genetic infant, no? And so with this project, we do the digital copy from the image of the patient. And on the HPC, we do hundreds and hundreds of possible surgery. Why? Because we compress all this data, we use AI, we use a reducer order model, and then we put in the hands of the surgeon an interactive model to understand what's going on. And in that case, for instance, about the HPC, with a Formula One car, you have 1 week because you want to win a race. No? In that case, you have 24 hours because you have to save a life. No? And we managed to package all of this in 8 hours. And we worked together with Cineca, that is the National HPC Center in Italy, to make this working. And it was a lot of IT research also, because even optimizing all the communication of the data, it's really paramount. It's really important. So, I think I of course, I deliver classes, about CAE, and I have a slide. And in the first row, I start with, we have Excel, Word, PowerPoint, the email. Now we have ChatGPT as well, the MATLAB, and then Nastran, and you go up. And then in the advanced side, coding ability, IT ability. So I consider that is very important. Connecting to a Linux server and you have so much power, is that easy? No? So you need also this kind of expertise. And for me, that I'm a mechanical engineer, I have a software company. So I in my, also in my personal knowledge, I now quite expert, as you can hear, about computing, but it is not something that I have studied at the university or in my PhD. My PhD was about traction mechanics. So a different topic. And today we need more about a super knowledge on IT, and now the knowledge on computer science as, for instance, principal orthogonal decomposition was something not in my expertise. Today, we are using principal orthogonal decomposition daily. We use neural networks, we use AI. And so it's really crazy for CAE to put all these things together. Also, the language is different, because when you speak about the digital twin, if you see this on the perspective of the CAE simulation, one thing. If you see with the perspective of control engineers or maintenance engineers, so we did an implementation with Predix by GE. It's really complex story, but it's nice because you put together many things. Next year, we'll start a class that is digital twin modeling and applications. So specific on this topic. That is something new, because all the knowledge were there, but the way of putting all this all together changed a lot.
Yeah.
Because, I think that one important thing when we use AI, that we need the data. No, we need a lot of data. The more is the data, the better. And as CAE engineers, we are really smart data creators. So give me a model, give me a parametric model with mesh morphing is easy, and give me a lot of HPC power. Well, I will create your big data. So go with AI.
Well, thank you so much for that explanation, Marco. It's really exciting. I want to come back to the biomedical application. Sorry, I had a warning come up, and I just wanted to make sure our audio video was working. And so I lost track for a minute, but can you touch on the surgery application for the infant? And can you share a little bit more detail on how you're deploying a reduced order model, right? Am I correct? That's what you're doing in that situation, and how you're deploying that, and what the benefit is, and what it allows the surgeon to do that they would not have been able to do modeling.
I give an explanation. I think here we could add an image, no? Because
Yeah.
the workflow, the problem is that when we go with digital twin and medical digital twin that are based on CA simulation, we are exchanging information between totally different worlds. And so the good thing is that we have workflow that allow us to put the data, the high fidelity data results in the hands of the expert. So what we do and what we did for the Copernicus project, this is the name, is that we have a stage in which we interact with the medical staff. So the medical staff, they used to work with the images. They are happy with images. So they take the image and they say, okay, this is the problem. I will go putting the shunt that is a bypass pike, from here to there. And this is my first choice. This data, together with the AI, will be used to extract the anatomy of the patient, to extract the hint of the surgeon. And so we create the geometrical model and then the high fidelity mesh that is needed. Then on this, we use Morphing to change its height. We can rotate this, make it longer, shorter. And so we have 16 parameters. And in this parametric shape, we start to do hundreds and hundreds of possible surgeries. And this is totally in the HPC side. Once all the snapshots are there, we use a model reduction approach. In this case, we are using ANSYS Twin Builder that is able to receive all these snapshots. And taking the snapshot, compute the singular value decomposition, the principal orthogonal decomposition, and then put all this data that each design point takes many, many hours, maybe not hours, but it's a long calculation time, Allow to compress the data and make this data interactive. Once the data are interactive, we have a very powerful technology that are the functional mockup units using the functional mockup interface technology that is very well established in this field. And so we can create a dashboard where the data can be interacted. At the moment, in Copernicus, we deploy the data simply in a tablet, so you can touch and see. Now we have the same experience available in the VR, so you can touch and see what's going on, and it's responding real time. So one good thing I think of this digital twin technology is that allows to move information from the expert hands of the CAD designer, the CAE analyst, the aerodynamics expert, and so on, into the hands of the people that has totally different expertise, like the medical doctor, like the medical staff. But we are doing something similar in aero development, because in the aero development of a car, we want the car, you buy a car if the car is good, if the shape is good, not because the aero is performing perfectly. In the aero department, we have a super expert to improve performances. And today, what they did is that they take the ideas of the style, but in style, it's not that common that you have engineers. Usually you have artists, because the car is masterpiece.
Gotta be aesthetically,
With this technology, we're doing something similar, because we take the idea of the style, we do the data crunching, and we put the interactivity, and so the flow results, the drag, the lift, directly in the style software and the style tools. So I think that it's a very good way of moving information. And also, of course, for the medical application, you have now, I think it's one of the field where this is really, really compelling, because you see the value, you see the benefit, the in silico approach is very well established, but what is difficult is to have the daily practice benefit of this. And so it's clear. We have clear goal. And I don't want to call this a business. No, healthcare different. No, it's more a mission. You are saving life. No, so we talk about business model, but it's bad to say a business model about the health. But this B2B2C, because it's a B2B2C model, can be extended to many different fields. For instance, we have demonstrator in which you can scan the body of a cyclist, no? And then you can put an helmet that perfectly match the shape of the body to have the minimum drag. This is typical for time trial, no? So if you have an aero bike, you are an hero, you are an Ironman hero. I have so many friends doing this. So it's not the Olympic sport usually, but it's more your passion for the sport. And it's an interesting market. And going there, so with sport equipment, going to be user specific rather than patient specific for healthcare opens so many different things. So let's say that with this technology, you can put the tool that, let's say that putting the Aero and all the CFD could be useful, but could be also a way of selling something. No, because at least it's nice to see. There are many open doors that are opening using this. And I think that the translation of the data from a word to another, it's really a very important point. And this is why, as RBF now, we are also joining the FMI, FMU. RBF Morph is going to be listed there because now we are supporting this file format, as all the other vendors are doing, Altair, ANSYS, and so on. And I think it's really exciting for CAE, generally speaking. For CFD, of course, is interesting. And it's something in which all the actors today are really active.
I must be out of the loop. What's FMI, FMU file format?
Yeah. So FMI stands for Functional Mockup Interface. Okay. And it's a protocol that allows you to put or a dynamic model or an interactive static model exposed with an interface that is always the same. So you have an XML file describing what the technology can do. And then you package everything into a library. Could be a secret library, could be the source code, but it's a way of creating interfaces between things. Yes, in the same approach, you have the Modelica platform to put all together. Okay. You can access them with MATLAB, with Python, and with devices. No, so also the code on the device that can use these.
So it's not just, we might be familiar with multi-physics coupling. This is primarily for multi-platform interaction.
Yes.
Or multi-program, I should say program interaction.
It's intended for exchanging whatever. So it's good, of course, for multi-physics, but you can do whatever. Yeah. And it's a very interesting way to make the information portable. I go with a very specific technical example. No, as I mentioned, we have a good experience with ANSYS, and with ANSYS we work with both CFD, fluent mainly, or CFX somewhat, and with structural solvers, mechanical, the solver under mechanical APDL that can be used standalone, but also LS-DYNA for crashworthiness that has been recently, not that recently, 2 years ago, acquired totally by ANSYS. Yeah. And you can do the simulation with this tool. Of course, you can use also other solvers, and you can use the Twin Builder platform that is an easy deployment to create the raw data. No? Okay. Of course, you can do that with Python. You can do that with MATLAB. But with Twin Builder, it's you have the UI. It's easier, to create this information. And Twin Builder, as other platform of other vendor, can once created the reduced model, can export this model into this file format, into a functional mockup unit. And the functional mockup unit is a standalone piece that allows to receive input and give out output. And what we have done, I have some nice video, maybe we had them later, like I'm speaking. Because I think we are the first to have this technology. Is not yet on the market, but it will appear soon. So we have created a way of translating such functional mockup units that today speaks Linux and Windows. So you have the SO and the LL. The problem is that when you go into the VR, if you go with the MetaQuest 3 that we support, you have Hype because it's Android. If you go in the Apple Vision Pro, you have the Apple OS, no? And so the problem is that the FMU are not yet exported with this data inside. So in our software, we created a kind of translator that read in the FMU and put out the FMU that are able to speak more languages. Okay.
Okay.
And with this technology, we put the FMU in the DR in a wireless way. And for instance, we can create the interactive design of the car, Aero, no? But if you put just the car, the mesh of the car and the colors, it's good, but it's not that good. So we can put the car into our RBF auto salon, that is like a salon for selling car, and it's way better, especially if you are in the VR.
Okay.
Yet you can put object on the car to control it. So it happens that you drag the surface change under your hands, and the color of the pressure and all the data change in real time. And we go up to 60 frames per second without problems because the data are compressed. We load the FMU to the GPU of the VR, otherwise you are not so fast, and you are there. We already did a test with the Apple Vision Pro. It's not yet supported. It's not yet in the market, at least in Italy. This is really something we are really excited about it. And we are envisioning also this kind of application for the healthcare. There are surgeons in Italy that are already working with the Apple Vision Pro, because to wear the VR into the surgery, you need really very high quality, and the quality of the Vision Pro is outstanding. It's up to the one of the high-end professional ones. And so I think that what was science fiction some years ago, now it's something that is happening about this.
Yeah. And I want to transition. I think this is a nice segue to trends that we're seeing, right? I'm sitting here thinking, I've done a few of these interviews over the past 6 months. Probably most of the interviews on the channel have been within the past 6 months. And the thing that I'm really excited about and astounded to see is the change at which these developments are happening. As a learner, as someone who's quite new to the field, really, considering how long this stuff has been going on, the changes are just exponential. And how fast these developments are happening. Like you said, what a few years ago would have just been science fiction is now becoming possible. So what gets you excited? Like when you look on like a vision of where you see your company going, but more generally too, where you see the field of CAE going. I know we talk about digital twins, but what specifically gets you excited about simulation opportunities? And what do you see as the largest opportunities for simulation?
Yeah, this is a very nice question. Indeed, the pace, of the CE market changed decade over decade, and it's always stepping, because what was in the past available just for the super expert, no, even staying to the design world, have been a lot democratized. No, we need tools that are super specific, but we need also tools that are not that super specific. It comes with some risk. Because it happened on time to contribute on LinkedIn on an automatic AI generated expert page about FEA and things like this.
Yeah.
And there are situations in which the topic itself is wrong, no? Because FEA is not what you do. FEA, it's a tool to do structural analysis. So you need to be an expert of what you are doing. So yes, we have tools. So we have to take care about this.
But I love that distinction. Thank you.
So what's happening is that the business model also is changing, no? Because previously the typical usage was having everything in house. Now we are doing more and more on the cloud. There are solutions that are on the cloud, and that's all. For instance, Ansys recently launched the Sim AI. Sim AI requires a lot of data crunching, and it's on the cloud for the computing. You can go there. No, we have that at the same time. The tools are changing. The resources are changing. We have now in the future roadmap also the quantum computing. And so we have to understand what will be the impact of CAE, because CAE was first, you do the CAE for a design, then we do the CAE and we consider robustness, not just the optimization, but even you have decided one part and you do 1,000 parts and they are not the same. So you want to understand this. So we are, of course, using more and more the simulation, and we are moving beyond and beyond all the barriers that we had. So the spread is really wide, and it's wide even if we limit this into the industry, because there is a lot of competition. The product we are using today also for this interview, no, a gear that I think is simple, affordable. But let's think about this 20 years ago. We are going with 4K recording, with this high band, no, everything is perfect, no? And for us, it's normal, no? We drive a car and the car works for hours, so much, everything is always working, almost, okay?
Sure.
Yeah, and but we have this high level of reliability of everything, because whatever is done has a lot of this CAE analysis under the hood. And what's happening now, and this is why digital twin, why there is so much interest, because it's useful, but because it's opening really a new business that will grow more and more, the business of CAE. Because one thing is that you design the product. Another thing is that you are the product. Because when you go, for instance, let's take an example. You have the generator, no, for the wind. No, you have and you have to design it. You have to compute the bearing, the wing is very large. You use composite and everything, and you will use your CD stage. And maybe you decide, many companies are doing this, that want to use the CAE when a component is repaired. So you have the CAE model ready to go. You have the repaired part that is a little bit different. You send back the information, you recompute, and you get there. So one more usage of a CAE because it's used for maintenance. But when you have that, all the logic of the CFD of all the farm has been computed with the CFD, for instance, and has been condensed into this FMU and becomes a part of the product. No, for each wind generator, you will sell this knowledge. You put this into the hardware. No, and what changed is that, for instance, if you think to a car, no, we have all our cars. There is one, okay. They have the digital twin inside. So when you are driving, no, if you do something stupid, no, the car will save you, no, because it will record the trajectory. Now with the ADAS, it will brake and so on. But how is doing that? Because in the ECU of the car, there is the digital twin of the car itself that in real time is doing exactly the same thing. Also the stupid ones, no? And so if something is going wrong, it's not waiting, it acts, no? And what is the difference today is that for the ECU of the car of 10 years ago, the software is there, was written by hand. So you write down all the equations, because if you want to be real time, you can't afford to use high fidelity simulation and all this data and all this too. Today, we can do that because we use machine learning, AI. We create the data with the simulation. We can compact the data. And so you have the simplicity of a simple math equation without the equation itself. Because if you see the equation, what is the equation? It's a complex neural network that has been trained to do something. But all in all, it's doing the job. I think that what is really a promise for us is to understand and also with fantasy what could be the possible products. I have some. Let me tell you some of the ideas and the prototype we developed. For instance, the case of the helmet, it's something that will say simple. The business model is interesting. We are active on now nautical application. One of our engineers is super expert. And one application we want to do is that while you are sailing with a VR, you can see the sail with all the fluids and everything, so that when you adjust, you see what's going on. We are thinking about smart incinerator for the waste, because the problem is that you have to be sure that everything is burned, no? But you can't see what's going on, no? We developed a prototype in which, using this training technology, you can superimpose, no, on the actual data of a movie, and so you can tweak and control. We did the same for the HVAC for an operating theater, no? And it's a way of putting the simulation is not about how to design things, it's about how to help the thing to work. Another very interesting project that I love, and I really hope we will have a chance to bring this and move forward, is about the smart cooking. The smart cooking means that you can do the CFD simulation, for instance, of the Thanksgiving arcade, or of a bread, of a pizza, no? And using this ability of changing the shape, you can have the small pizza, the large pizza, and so on. And so you can have that. Let's figure out that with your app, you see your cooking going on, you see what's going on inside the food, and you can decide, or you can let the software decide if it's cooked or not. So there are so many possible things for which simulation could be delivered. But another thing could be about doing smart HVAC in the car, no? Because now you have a very powerful HVAC system, no?
Yeah.
But the automation that you have is not receiving that much feedback, no? It's just of temperature. So let's imagine, for instance, today it's quite common that you have a camera watching you, and usually you do that to be sure that you are you are driving, you are not sleeping. No, it's about your attention. But the same technology could understand if you are happy or not with the climate that you have, and so could adjust in real time. And all of this can happen with the simulation. We completed the demonstrator in which we used in the simulation morphing simply to adjust the movement of the fin, no? To make the actuation model computed and reduced to work in real time. And this will allow to create the logic to get there. So there are really many applications. So I think that as told, the B2B2C, it's really the largest market we can address with this.
One question I have that has been on my mind, I'm really a fan of the writer and thinker Greg McKeown, and he wrote a book called Essentialism. And I just wanted to get your take on this. The premise of the book is, in our day and age, we have so many options that it becomes even more important to focus on the vital few, right? You can do anything, and you just listed tons of ideas that are exciting, that are really neat. And as simulation opens up faster computers, faster compute, better algorithms, just we have so many options. I just wanted to get your thoughts on, I think the way Greg puts it is, you can do anything, but you cannot do everything. And so what is your take on that? Like, when you look at, we only have a limited time of a career or a life or the opportunity to build something. And so how do you make those decisions? And what things do you think are going to come into play? Because I guess where I'm going with this is, and this is maybe a bit poetic and too philosophical, but like T.S. Eliot's, where's the information, or where's the knowledge we have lost in information and the wisdom we have lost in knowledge, right? We have so much data, so much opportunity, that are you worried about people missing the mark and being focused on problems just because we can, rather than maybe some of the real value problems. And it's just a thought, just curious on your take, because it's something that I see I get excited about, but then I have to remind myself I can't do everything I want to do. And it's a constant reminder, right? There are so many subjects, so many things that I'm interested in, and you just can't do it all.
Yeah, I think that the things are really easy about this because all in all, what you can do, no, you have, as you mentioned, you have a time, but also daily, you have a certain number of hours. And so what will happen, it's really natural because you can't afford to do things that will not bring back value.
Yes.
It's easy. What is really important, of course, for me as Marco, but also for my company, no, and for the team that I have at the university. Of course, you need to leave some room for the ideas, for the fantasy, and so on.
Yes.
And we are also helped to get there. Why?
Yeah.
Because, of course, if the problem is the pace of the business, no, you have to stay on pace, otherwise you fail.
Yes.
But we have some apps. One app is that if we have enough fantasy and we can involve our customers in doing something that is new, no, but they know it's useful because otherwise they will not invest with you in there. So this is the first part of the answer.
Yeah.
So once, for instance, the smart cooking idea was not something just by us, was something by a large group. Okay.
Sure.
And even in large group, there is interest to do something that is visionary. No, it's important.
Yeah.
And on the other hand, you have another way of moving there. That is, you have the ability to have different kind of customers in your company that are typically public fundings institutions. So in Europe, we have the European community. It allows to get resources to explore. Of course, you can't explore what you want, but consider, for instance, a project as the Copernicus one. It was not that large, but we got, I think, 300,000 euros, no?
Sure.
For 1 year. It's something that can't come easily from a customer because it's something to be explored. To be a little bit visionary, you have also this kind of help. And for people like me in a position in which I stay, of course, in the industry, we have many customers. We work with the pace of with the time of the customers, with deadlines of the customers, no? But I am a professor at the university and I love to do synergy. And the synergy means many different things. It means that you have undergraduates, young students, PhD students. We have many people that are coming from other universities across Europe, especially. So in this situation, you have big opportunities because you can explore something if it makes sense. And also you can have all this new knowledge in a new career, new passion. So this is something that I love to see.
Yeah.
You saw in the career, there are different stages, no? There is one stage in which you want to learn everything. The other in which you want to go up and have success, no?
Yeah.
But when everything is there, no? You think about what's happening around you. And it's really, for me, seeing the people, no, that started with me, worked with RBF at the beginning, and now as a leading position in different company, institution, and so on, it's the maximum satisfaction, I want to say. So I think a little bit wider answer to your question. But what I'm saying is at the beginning of this interview, you told me about the technological transfer, what can we move and what not.
Yeah.
We know it because there are good ideas that work. There are good ideas that are just good ideas. And that it's natural. Unfortunately, it's natural. And what is really important, but of course, this is typical also for the startup world. It's really important that you are able to start and able to understand that it's the right time to quit. And
Yes.
with a
Yes.
new adventure, it's really important. And also that you learn it from your experience. I told you that my first experience as an entrepreneur was a failure, and it was a pity. We have a famous driver on it was very interesting, but the market was not the
It's
right
not
one.
there.
It's really important that you learn. And about all the flowers that you can pick, there are so many. Of
Yeah.
course, you need to understand wisely what you do,
Yes.
because you have also another important thing is that it's not just a matter of working all the day. What you do must be rewarding, and you need to have also create a good relationship with the people.
Yeah.
So I think this is important. For me, we have a network of alumni that is really wide. And next week, I will go for a dinner with people that graduated 20 years ago. So I think that it's important also what you can create with the people, no?
Yeah. Yeah. Wonderful. Wonderful answer. Yeah, that's very insightful. And I definitely agree. I've personally, it doesn't take long when you've got a revenue driven feedback loop, you can't lie, right? You can't lie to yourself
Exactly.
about when something's going to take off if the feedback loop's revenue driven. So that's excellent. Just to wrap up, to get the full picture of, are there any situations that you wouldn't recommend using morph methods, and why? Why would those be situations that maybe it's not the best fit, right? Each simulation tool has its place and its strengths and where it really excels. And it all comes with trade-offs. Just to round out the
Yeah.
picture.
This is a really very good question. When we focus on design, what is typical if you want to invent something new, and once you have some concept and you go with the CAE, what is typical is that you want to first understand what is the right topology, no, the architecture. And in large projects, this is typical because you have the preliminary design review stage, the architectural design review stage. So if you go in large project, you have this organization, you can't move from there. And once that the design is frozen, it's frozen. So you can change thickness, you can change something, but if you change too much, it's a mess. Why? Because a complex system, for instance, a car, you have so many subsystems to arrange that you will destroy all the packaging. Okay. So morphing is something that can be used at even a very first design stage. It's not a matter of the amount of change. You can also change a lot the shape, but it doesn't allow you to change the topology. So for the situation, I have a very simple example. We also published a success story because we were active on the design of the M10 engine. That is a very special one because it's the first time that rocket is propelled with liquid metal. So the problem is that the distribution of the fluid is very critical, and the pressure drop were too high, and the 3D printed prototype was perfectly in line with the CFD. And we put our optimization in this. The problem was that it was not just a matter of deciding how many nodes to do and how large to do, but the problem was, should we use 6, 12, 18? No. If you change the number, it's a matter of topology. Or propeller. No. Should we use 3 blade, 4, 5, and so on? The machine can't solve everything. There are tricks, for instance, in the case of the engine that I have mentioned, we use the trick. So we created the model with the 16 holes, and then we made an analysis with all the 16 holes open. Another in which half of the holes were changing, internal boundary condition were disappearing. But it's a trick. First of all, morphing can't be used when you want to change topology, unless you know that you have 3 options. So you can do the 3 options, and with morphing, you make all of them parametric. It's possible.
Okay.
There are situations in which morphing will destroy your mesh. There are applications that are really good to do with morphing. For instance, I don't know if you hear about the problem of porpoising of Formula One car. Porpoising, you need to do a transient analysis to understand the stability of the car. And moving a car up and down, despite the fact that, beside the fact that the model is huge, so it's very complex on the setting up this, there is the problem that you have a clearance, no? And if you are closing a clearance, the morphing can't work because you can't make cells appear or disappear. So what you do is that you do the baseline mesh in the middle so that you can squeeze or you can stretch. But if you go too much, your model will be not good anymore. What you could do in that situation? There are situations in which you need to use something different. There are many methods. You can use immersed boundary. You can use chimera meshes. There are many. But all in all, if you see today, the standard is still the body fitted. No?
Yeah.
Okay.
Yeah.
And there are also situations in which you like to use the morphing because you want to compress the data, because you want to principal orthogonal decomposition. So in that case, morphing is not the complete solution because you need the remeshing, you need to create a new mesh, but you can combine them together. You do the variation, you do the morphed depth, faded mesh, but are faded cells, not the nodes. The nodes are good. You do the bad mesh, you do the new mesh, you compute the new mesh and you remap on the bad mesh the results. And so you can do in any case the POD. It's very complex. We used to do it when it's needed.
Yeah. Okay.
Or there are situations in which you are not using the morphing to have something that have to be compressed or have to be transient, but you can simply rely on a shape. So morphing could be a part of the remeshing process. So you morph and then you activate a remeshing tool that takes the bad area. It's possible.
Yeah.
You lost the topology, the isotopology between the two mesh, but if you don't in, that can be done. Morphing is very useful. And what is also something that I want to add about morphing? We started for doing parametric shape investigation, no? And I remember at that time, a friend of mine told me, Marco, consider that what we need today, Formula One, would be the need in 3-4 years of all the automotive industry. Because usually Formula One, it's really demanding about methods, and performance. But what happened later is that many new drivers appeared and were very good for us. First one was the additive manufacturing because of the expiring of some patents changed a lot 10 years ago. When you have the flexibility of do whatever you want, mesh morphing is very useful because you can represent shapes that are not possible at all with standard CAD system. So this has been a good driver for us.
Yeah.
And in the more recent time, the use of morphing for parametric shapes, for creating reducer order models, but also now with these AI tools that are able to learn from the data, to be precise, you need more data.
Yeah.
Even if you have many different topology, if you want to create more data between the topology, morphing could be used. Well, it's not the solution for everything, but we started in 2009. We are in 2024. We are still doing business. So it's it's a very small niche, but it's a niche that is become important. I remember last year in one of the presentation by Yancy's CEO about corporate trend and all what's going on. So many placeholder about the technology, solver meshing, and so on. And there was a placeholder for Morph. Something we are good at. And it's still growing and be interesting for what's happening in the CAE industry. So
thank you so much for explaining the story of founding it. I always love hearing the stories of how they were founded. So thank you very much for sharing that. I really enjoyed it. So thank you so much, Marco.
Thank you for your time. It was a real pleasure.
Yeah, really appreciate it. Thank you. Thank you for listening. Really, thank you. Did something about this episode stand out to you? If so, please go ahead and share it with others on LinkedIn or other social media so they can find this as well. See you next time.